Hello students and friends. In this video I am going to solve the question number 7 of the sample paper of 9701 paper 4, which was given in the year 2022. This question number 7 consists of questions taken from transition elements and a question from electrochemistry. So I'm going to discuss the answers in detail. So please stick around with this video and try to understand each and every answer. Please ask your doubts in the comment section, and if you like it, please give it a like and share this video with your friends. So starting with the first question, sketch the shape of a 3D XY orbital. So you have to draw. They have given you these three axes, x, y and z, and you have to draw the shape of a 3D XY orbital. Now this is how the different d orbitals look like. You know that there are 5 of these d orbitals, and we have to write about, we have to draw the xy. So xy means that these lobes, which are the probability regions, these lobes will be in the xy plane, and there are 4 such lobes, and they are in the xy plane. So you can see that the xy plane is the plane, is a planar shape which lies within the x and the y axis. So these lobes will be in that particular plane, and that's how you draw the 3D XY. Just to tell you that if it had been a dx square dash y square orbital, in that case the lobes would be on the axis. Here the lobes are in between the axis. Here the lobes will be on the axis. So x square y square means that the 2 lobes are on the x-axis and the other 2 lobes are on the y-axis. 2z square is that there are these 2 lobes on the z-axis, and this is also a probability region whose details you don't have to understand. So this is what you have to draw as far as the shape of the 3D XY orbital is concerned. Then we go to the next question. Some transition elements and their compounds behave as catalysts. Explain why transition elements behave as catalysts. So the simple answer is that it is because transition elements have more than one stable oxidation states. So that's the answer. You know about this. Different oxidation states exhibited by the transition elements. Like for example, manganese has several stable oxidation states like +2, +7, +6 and so on. Now the next question is that catalysts can be classified as heterogeneous or homogeneous. Complete table 7.1 by placing 1 tick in each row to indicate the type of catalysts in each reaction. So the first reaction is Fe in the Haber process. So obviously you are supposed to know what the Haber process is. So I'm going to remind you about that. What is the Haber process? This reaction is the Haber process. Nitrogen gas, hydrogen gas combine to give you ammonia gas, and Fe is the catalyst. Here Fe is the solid, whereas the reactants are gaseous, so it represents a heterogeneous catalyst. In this reaction, Fe2 plus I minus all are ionic and they are all in the aqueous state, so it is homogeneous. In NO2 in the oxygen sulfur dioxide is gaseous, so also NO2, so all are gaseous. So once again this will also be the example of homogeneous catalysis. So we go to the next question, and this next question is based on electrochemistry. So let's go through. A solution containing a mixture of Sn2 plus aqueous and Sn plus 4 aqueous is added to a solution containing a mixture of Fe2 plus and Fe3 plus ions. Table 7.2 lists some electrode potentials for the electrode reactions, and E naught from the data can be used to predict that which reaction takes place when the two solutions are mixed. So I have ticked those reactions which are of significance. One is the Fe2 plus Fe3 plus, which is this one. The other is the Sn2 plus Sn plus 4, which is this one. You can see the standard electrode potentials. This is plus 0.77, this is plus 0.15, and you should know that the electrode potential which is greater acts as the positive electrode and the cathode, and this represents a stronger oxidizing agent. So that means Fe3 plus will undergo reduction, so the reaction will take place in the forward direction, whereas this electrode potential being lower, it acts as the anode, the negative electrode, and oxidation takes place over there. That means that Sn plus 2 will be oxidized to Sn plus 4, so this will be reversed. This will be in the backward direction, whereas this will be in the forward direction. So if you add it, then because there is only one electron here, so multiply this equation by 2, and then because this reaction is reversed, so the Sn plus 4 goes on the right side, and this is as it is. So this is like Fe3 plus, so this Fe3 plus will change into Fe2 plus, and Sn2 plus will change into Sn4 plus. You have to multiply this by 2 to balance the electrons, and the electrons get cancelled. So this is your final equation, where Fe3 plus ions are reduced to Fe2 plus ions, and the Sn2 plus ions are oxidized to Sn plus 4 ions. Let's go to the next question, where you have to calculate the E naught for this reaction. The correct formula to calculate the E naught cell is that you have to subtract the anode from the cathode. So anode is the negative electrode and cathode is the positive electrode. So the higher minus the lower also works. So 0.77 minus 0.15 gives you the E naught cell of 0.62 volts. Hope you understood this. Let's go on to the next question, which is based on transition elements and the stability of the complexes. So hexa aqua ion 3 are pale violet. They form a colorless complex with the fluoride ions. So when the fluoride ions get added, it forms a colorless complex, and a deep red complex is formed with the thiocyanate ions, which is equilibrium 2. And they have given the stability values for both the reactions. As you can see, this is 2 times 10 raised to 5. This is 1 times 10 raised to 3. So the first one has got a higher value, which means that this complex, the colorless complex, is more stable than the deep red complex. Alright, so now the following two experiments are carried out. A few drops of KSCN are added to 5 centimeter cube of Fe3 plus, followed by few drops of KF. So when you add KSCN, you will get the deep red complex, and when you add the F minus ions from KF, it can form the colorless ions. And now the colorless complex is more stable than this, therefore the color will change from colorless to deep red. First you formed a deep red complex, but the colorless complex is more stable, so the deep red will now change into colorless. So the less stable complex will change into a more stable complex. But in the second experiment, when you already added KF, you are forming a colorless complex. Now the red complex is less stable, so the colorless complex would stay colorless and will not change into the red. because the red complex is less stable. So these will be your observations, and the reason is related with the stability, the equilibrium stability values, which you can see over here. Okay, so what is the name of the reaction taking place? Obviously it is a ligand exchange or a substitution. The last part of this question is that the solutions of iron 3 salts are acidic due to the equilibrium shown. So you get the H plus ions formed, so it is acidic and there is an equilibrium, that means it is a weak acid. The Ka value is given. Calculate the pH of 0.25 mole per dm cube FeCl3 solution. So this concentration refers to the concentration of this complex, and because it's a weak acid, you have to recall the formula that the concentration of H plus is the root of Ka times C. Put the values of Ka and the value of C, take the square root. That gives you the concentration of H plus. Then you apply the formula of the pH being negative log of the H plus. Negative log of this value gives you a pH of 1.8. So that's the answer. So I have discussed question number 7 of the sample paper. In other videos I will discuss the other questions. Thanks for joining, and if you like the video, please give it a like and comments. Thanks for watching.